here is use the conversion formulas. Let me write them down on the top. So because we're going to refer to them every once in a while. So x equals r cosine theta and y equals r sine theta. And well, so all we have to do, I mean, it's pretty straightforward. Just substitute wherever they correspond, wherever it corresponds for x, whatever it corresponds for y. That is 2x, well, in this case, x is r cosine theta plus 3y, which is r sine theta. That equals to 5. And well, in this case, the idea is to transform an equation y equals f of x into an r equals f of theta. In other words, all we have to do is solve for r. In this case, notice r is a common factor. 2 cosine theta plus 3 sine theta equals to 5. And divide both sides by this whole quantity. So r equals 2 cosine theta plus 3 sine theta, everything in the denominator of 5. And that's how the equation looks like for polar equation, for a linear equation of this form. All right? And again, I think it's pretty straightforward. It's very formulaic. I mean, just substitute where it corresponds. That's all it is. Let me make some room over here. All right. So, well, the next equation, 6xy equals to 7. Well, this one is going to be like some sort of a special case because of the format, because of the way that this equation will look like. Well, essentially, so that's a 6xy. Well, again, x gets replaced with r cosine theta, and y gets replaced with r sine theta. Equals to 7. And that's all we do. That's it, pretty much. So in this case, how is this going to be different from the other one? Well, number one, let's do some simplification. So we're going to multiply the r's. That's going to give us r squared for 6r squared cosine theta sine theta. And for now, we're going to solve this equation for r squared. And we're going to discuss what's going to happen in this case. So r squared equals 7 over 6 sine theta cosine theta. And well, in this case, we're going to leave the equation the way it is, like this, in explicit form. I mean, in implicit form, because if we solve for r, what we would obtain in this case is the following. We would have to get two solutions. Essentially, r equals plus or minus the square root of 7 over 6 sine cosine. All right. Well, in this case, you don't want to express this as plus or minus. So when you submit your answer on the WebAssign, make sure to have it in implicit form in this case. All right. So let's see what's next over here. So what was I thinking of this anyway? All right. So the next example. The quantity x minus 1 squared plus y squared equals to 1. We need to convert that into polar. However, yes, even though it looks like pretty straightforward to just substitute x equals r cosine and y equals r sine, I wouldn't recommend you do that because you will have to expand a binomial or FOIL containing sines and r. So my advice in this case is that square the binomial right now while we're still in rectangular form, and then substitute the identities. And in fact, it's going to be a lot better. You'll see. So I'm going to expand this binomial, and x squared minus 2x plus 1 plus y squared equals to 1. And well, so putting some quantities together, so let me put the x squared and the y squared together. That is x squared plus y squared minus 2x plus 1 equals to 1. Well, actually, we can cancel out these ones. And leave it equal to 0. Well, so there's a couple of substitutions that we're going to do. So in this case, I know what you might be thinking. Write r cosine quantity squared, r sine quantity squared. Well, we have an easier identity for x squared plus y squared. Recall that essentially the Pythagorean theorem for polar coordinates tells us that x squared plus y squared equals r squared. And in this case, well, we can just replace this with r squared and replace x with r cosine theta right here. All right, so that's gonna leave us with r squared equals to, r squared minus 2r cosine theta equals to 0. And well, we still have to keep solving the equation to keep simplifying the equation rather. So that's r squared equals to negative, or rather positive, 2r cosine theta. All right. Well, so we can still simplify this a bit further. However, let's make a contrast with something we have done in algebra versus what we're doing here in the world of polar equations. So for example, okay, anyone, question for anyone. How do we solve this equation? Divide both sides by x, okay? Okay, divide both sides by x, and that's going to leave us with x squared equals to 1, right? Which is x equals plus or minus 1. So how many solutions do we have over here? But the equation is at degree 3, which implies that we should have 3 solutions in this case, right? So, I mean, even though it looks natural to divide both sides by x because, I mean, it's sort of natural, well, however, we can't do this. And that's because when we divide both sides by x on an equation like this, we are potentially, well, we have two issues. Well, number one, we are missing one piece of information. And number two, we are potentially dividing by 0. So the correct way to solve this equation rather is to, okay, x cubed equals to x, is to set the equation equal to 0. X cubed minus x. Set it equal to 0 and solve it by factoring x times x squared minus 1, and that's x times x minus 1, x plus 1. Solve by factoring. How many solutions are we going to have now? 3, right? And one of the solutions happens to be 0, right? So doing this, careful with those kind of pitfalls. So you don't want to divide by 0, and you don't want to miss one piece of information. All right, so x equals 1 and x equals to negative 1. Well, it turns out we cannot do that in the world of rectangular because, again, we would have the issue of dividing by 0. However, this is a valid move. This is a valid move in the world of polar. We can do that because, well, the radius can be 0. It turns out the radius can be 0. So, and in this case, that's going to take us back to r equals to 2 cosine theta. And in fact, if you noticed, this example matches exactly the same solution as in the previous part. All right. So we just all we do is just do it backwards. Yes. Should be r. Thank you. And this is final answer for this one. All right, what's next? A little bit more of algebra with, well, or geometry, analytic geometry with polar equations. Well, so these are the graphs of the common polar curves. You don't have to memorize these graphs. You don't have to know them. You don't have to write anything down if you're writing notes on your notebook. It's only a summary. It's only it's a picture of the different graphs that we can obtain using the polar mode on our graphing calculator. I'm going to show you a few, and well, different ways to graph circles. For example, r equals a, like r equals to 5. That was like the first example we did. That's the circle of radius 5 and center at the origin. Whenever you see r equals a sine, like for example 5 sine theta, 7 sine theta, notice Notice the circle is shifted vertically, it's shifted up. That's because, well, if you relate this with the coordinates of the values of the trigonometric functions, notice the y-coordinate represents the sine function, and well, no wonder why we have this shifted in the vertical direction, as opposed to r equals a cosine theta. So if you look at the points on the unit circle, it is the x-coordinate that relates the horizontal, the cosine function. So no wonder here we have a horizontal shift when we have an r equals some cosine theta. And well, this is another kind of function, that's the spiral. And then the next classification of graphs are limazones, like the cardioid, another limazone. This looks sort of a circle, but it's called convex limazone. But the most interesting ones are the roses, and well, it depends on what we have inside of the angle. That's going to tell us how many petals the flower will have, for example. And again, you don't have to memorize it, you don't have to like know this by heart, but it's only a pretty cool pattern recognition idea, you know. So we are going to have r equals a sine or a cosine of n theta. So whenever n is odd, for example, if we have a cosine 3 theta, for example, well, that flower will have 3 petals in this case. However, whenever the angle is even, or the multiple of the angle is even, for example, here we have a 2, well, the number of petals will be twice as many of this coefficient. For example, notice this cosine 2 theta has twice, in this case has 4 petals. This cosine or 4 theta, well, that one has 4 times 2, that's 8, and 5 in this case, it's an odd number. Well, that remains whatever number is. All right, so I'm gonna go to the graphing calculator to show you how to graph some of this. And all right, so number one, you want to make sure on your graphing calculator that you are in radian mode, and make sure on the different ways to represent function, you're in polar form. And then from here, well, just type the equation on your y equals, which in this case it's going to be equations in terms of r. And I'm going to make something up. I'm going to do 2 cosine of 6 theta. Okay, cosine 6 theta, well, that looks like a flower, but how many petals is it going to have? 12, right? Let's see if that's the case. Well, let me do some standard 6, and I'm going to zoom in a little bit. What? Zoom, standard, enter. Well, anyway, for whatever reason, it's not zoom 0. I'm gonna do, okay, that's zoom. Well, it looks a little sharp corner in this case. That's because of the window. So on the window, you might want to make the theta step in the same way that we did the t step for parametric equations, so we can see it in slow motion. So I'm going to ask the calculator to plot more points. So instead of doing steps of 0.1, I'm going to do 0.01 and graph. And that's going to give us a better picture, and it's a more refined, more stylized picture in this case, right? And well, of course, you can play with these flowers and the different equations, but also we have other fun curves right here that I got from online. We have like a butterfly curve. I'm going to do this one on the graphing calculator. So let's see. Let me go back to y equals. So clear, and I'm going to type e to the second e to the sine. Sine theta, and minus 2 cosine 4 theta. And let's graph. Well, I'm not going to be able to see the whole thing. Let me do zoom fit so I can see the whole graph. you will see the butterfly, the graph of a butterfly right here. And there's a bunch of pretty cool stuff that you can find online, like other graphs of even Valentine curves, Pac-Man, which I have over here as well. So the other ones, okay, there's this Valentine curve. Let me type that one. That one's a little tricky to type because of the functions that are involved, tangent and cotangent, and also this this absolute value bar. So let's see, let me clear. So for absolute value bars, you want to go to math, num, and that's absolute value bars. That's going to be tangent, theta, close parentheses, and raise it to the power that it's also an absolute value function. And well, in this case, notice we don't have a keystroke for cotangent, but we know from our identities that cotangent is a reciprocal of tangent. So I'm going to go like 1 over tangent theta, and close parentheses. We're done typing it, and graph. And well, in fact, for whatever reason, it's drawing two hearts. In this case, that one looks a lot better than the cardioid. If you look at the cardioid anyway, I mean, it doesn't really look like a heart because it's cardioid. It has sort of a shape of a heart, but it's not quite a heart. You really want a heart? It's this equation right here, all right? And well, there's a few more. Oh, the Pac-Man. Let me do the Pac-Man. Hopefully I can get it right because there's usually an issue with this one. So that's a 1 plus 1 plus cosine raise cosine theta, and close parentheses, and raise that to the 999 power. And we sort of have Pac-Man here, except for this sharp corner right here, which I haven't been able to fix, but essentially it looks like that Pac-Man figure, right? So, and again, I mean, you can Google a lot of these online, other pretty cool shapes, other even more elaborate like hearts, or what else? Hearts, other butterflies, other pretty cool shapes in there, all right? So, I mean, but again, you don't have to memorize any of this. All, if anything on the final exam about it, well, you will be given the graph. It's actually how we are going to apply these graphs, which is the next section, which is the calculus in polar coordinates. So in fact, what we're going to do is find the areas inside, or find the area of one loop over here, or maybe the 4 loops. Well, you'll see in the next section. All right. In the meantime, so that's about it for section 10.3. Let's go about section 10.4, which is officially our last section for the course. All right. And I think this section is going to take a while due to the length of the exercises. These are going to be long, so be prepared for this. But it's good. The reason why this is going to be really good is that we are going to review a lot of the trigonometric integration, which is something we learn all somewhere at the beginning of the semester, right? So it's good. It's good preparation for the final exam. All right. So in this case, we want to find the area under a curve described in polar form, all right? Well, so you know the whole story about finding the area under the curve. So the area under the curve under some function f of x within the intervals a and b, we got that area by partitioning the area into rectangles. Well, first we did the approximation to 4 rectangles, 8 rectangles. That became a tedious problem, and especially because it's in the end it's kind of a wordless calculation because we're not even getting a really good accurate result. But essentially, we went through the what we call the Riemann sum, which is a limit at infinity, which essentially what it does is add all those infinitely many areas of rectangles, so which is actually a lot better, a better, a better refinement. It's a refinement to get the accurate result. However, in this case, in order to find the area under the curve or inside a curve in polar form, we're not going to divide this into rectangles. That's not how we're going to do. In fact, finding the area inside of a region described in polar form relies on finding the area of a sector of a circle. And well, so the area of a sector of a circle, its formula rather, is given here, right? Area is 1/2 times the radius squared times the angle. And well, that's a formula you learned back in trigonometry or pre-calculus or even in basic geometry. And but in this case, this is what we're going to do. So for example, if we have a circle, let me do the case for a circle in a simpler way. So that's the circle, and I'm going to find the area of the sector. Right? And then the area of this sector, and then the area of that sector. Essentially, we are going to find areas of infinitely many sectors of a circle. Well, not of a circle, actually a region in general, because not all the regions in polar are exactly circular. So in this case, well, so this is our plan to derive a formula for the integral to calculate the area. Number one, so this area essentially, so area equals 1/2 r squared theta. However, the radius r is going to be the value of the given by the value of the function, you know, r of 45 degrees, r of 60 degrees, r of theta, whatever that is. In this case, well, that's a 1/2 r of theta quantity squared. But what about the theta in this case? Well, in this case, we're going to look at a delta theta. That delta theta is going to be the analogous of the delta x when finding the areas of rectangular shapes in this case. But no, in this case, the delta is going to involve the difference of these two angles right here. All right? So that's this is the partition here, the element of area, and essentially we're going to add infinitely many areas of those sectors. That is, in this case, the area or the actual area is approximately the sum from I equals 1 to n of 1/2 f of theta, quantity squared, delta, or f of theta sub I, delta theta sub I. That's you know, some width of, well, not a rectangle, but rather the difference. This width is given by the difference between the angles, right? But this is only an approximation. You want to turn it into area equals, which is ultimately what we want. So there's a big difference between approximately and equal. In this case, we'll take that sum and take the limit as n approaches infinity. Well, that's going to calculate the area of infinitely many sectors in polar. And well, so that's the integral of 1/2 f of theta quantity squared d theta, and in this case between alpha and beta. This, instead of saying A and B, we say alpha and beta. All right, and well, just take out the 1/2, which is a multiple constant, and essentially that's going to take us to this formula we have here. Another variation, well, instead of saying f of theta quantity squared, another way to say this or to express this is f of theta the same as r. It's the same thing. It's even more compact to express, and it's a lot more convenient. So how about we do one example of finding area inside of a polar curve. Let's do one example. Okay, let's be prepared with a bunch of trigonometric identities and stuff like that. All right. Well, so they're asking us to find the area enclosed by one loop of the four lead rows r equals to cosine 2 theta. All right. So we have the graph over here, and well, in this case, they're being nice and giving us the limits of integration for us. All right. So number one, let's write down the formula to set up the work to find the area. So area equals to, number one, 1/2 the integral from alpha to beta of r squared d theta, where in this case r is the given function to cosine 2 theta. Let me highlight that part. So r equals cosine 2 theta, that's going to go here. And well, that's 1/2 the integral. Okay, in this case they're telling us from negative pi over 4 to pi over 4, and that's a cosine 2 theta quantity squared d theta. Well, so let me simplify the parentheses. I mean, there's really nothing big that I'm doing here other than just cleaning up the parentheses. And that's cosine squared 2 theta d theta. So that's the integral we have to evaluate in order to find the area inside of one of these loops. However, there's a couple of issues here. If you evaluate this integral the way it's set up, I mean between negative pi over 4 to pi over 4, notice something. Notice the area below the x-axis is negative, while the area above the x-axis is positive. Okay? So we are going to have a little issue here. So this is negative, this is positive. Notice the symmetry at those areas, that's going to add up to 0. All right? Well, but it doesn't make sense that we get that because we are clearly seeing an area there, so it doesn't make sense that the result is a 0. And this is one of the issues. This is going to be one of the issues that you will run into more often than not when it comes to working in the world of polar. So well, what are we going to do in this case then? Well, so I'm going to take advantage of the symmetry of this region, and instead of calculating the integral between negative pi over 4 to pi over 4, I'm going to do half of it and multiply by 2. Essentially, I'm going to change this to 1/2 or integral from 0 to pi over 4 of cosine squared 2 theta d theta. And in this case, well, let me change some colors over here. So in this case, I'm going to integrate from 0 to pi over 4, but multiply this by 2. And that's going to fix the issue of getting a 0 area in the end. All right, so let's simplify this integral before we can start integrating. Notice how these two cancel. And so that's the integral from 0 to pi over 4 of cosine squared 2 theta d theta. All right. Well, so let's find a way to evaluate this integral. Well, so in this case, we cannot use a u substitution because, well, if we set u equals to cosine, the derivative is negative 2 sine 2 theta. But notice we don't have anything multiplying with the d theta, so we can use as a u du setup, unfortunately. So in this case, we will have to rely on trigonometric identities. And let me write those trigonometric identities. You might recall from trigonometric substitution, so we had a formula called, well, I usually call power reduction formulas, but textbooks typically relate it to half angle formulas. I prefer the power reduction because that name gives us a sense of simplification in this case. And let me write down those formulas. So cosine squared theta equals sine squared theta. Okay, does anybody remember these two identities? Mm-hmm. Cosine 2 theta. And what about the other one? Same but with a minus, right? So that's a 1/2, 1 minus cosine 2 theta. Now, careful, because, well, these identities, yes, they help us reduce the power at the cost of duplicating the angle, right? So that's what happens over here. But in this case, notice we have a 2 theta. Okay, I'm gonna make a mistake on purpose here, so to see if you can catch it. So that's 1/2, 1 plus cosine 2 theta d theta. So what's my mistake here? Should be 4 theta, right? Because if this is 2 theta, when we duplicate this, this becomes a 4 theta. Well, let's write this in terms of two integrals, all right? Writing this in terms of two integrals, that becomes number 1, that's 1/2 the integral from 0 to pi over 4 d theta plus 1/2 the integral from 0 to pi over 4 of cosine 4 theta d theta. And I think we're ready to integrate this one. So let me go over here below the identities. Well, the integral of the theta is simply theta, or 1/2 theta because of the coefficient, and plus 1/2 the integral of cosine, which is sine, and I'm leaving a space for that correction factor. When we integrate, that is 1/4. And this gets evaluated between 0 and pi over 4. So that's going, simplifying all this, that's 1/2 theta plus 1/8 sine 4 theta, all evaluated between 0 and pi over 4. And well, we have the integral essentially simplified. Let's just use the fundamental theorem. And that is, in this case, that's 1/2 theta, or 1/2 pi over 4, plus 1/8 for pi over 4. And minus, well, did you see what's going to happen if I plug in a 0 here? Well, for both terms, theta being 0 gets zeroed out. Sine of 4 times 0, which is essentially sine 0. Well, let me write it down anyway. 1/2 0 plus 1/8 sine 4 times 0. Well, this whole thing right here is going to get zeroed out. All this gets to 0, and well, these 4's cancel here. That's going to become sine of pi, but again, sine of pi is 0. So the only term that really survives here is pi over 8. So that's the area of one loop. All right. Now, what if we wanted to know the area of the whole flower? The whole for what would you do to get the whole area? Multiply by 4, right? So that's so the area of equals to the area, or 4 times the area of one single loop. In this case, 4 times 4 times pi over 8, and the whole area is pi over 2. Okay? That's what it is. All right? And all right.